folks, we're going to talk about the half-life phenomenon next, which is where elements and isotopes, which we've talked about in the previous video, become more stable by emitting radiation. But obviously the process is not going to last forever. If each atom is becoming more and more stable with each passing decay, so it gives off some radioactive particles, then it becomes more stable. Over time, a sample will become more stable. So as it decays, we say it has a lifetime. So here's my example. We've got an unstable atom. It's the nucleus that is unstable. So don't ever think that any of the outside stuff will be emitted, so any of the electrons never get emitted. It's to do with the nucleus. So in this case, we've got an unstable nucleus. It's wobbling all over the place, it's ready to decay, and when it decays, it shoves out, in this case, an alpha particle. So there it goes. And it becomes, from unstable, stable. So once it's emitted this, now this is a stable atom. If you had a lot of atoms that were becoming over time more stable, you could say that the number of unstable atoms is decreasing. Now, let's just say I had a box of balls, right, different coloured balls, and every time I picked a ball out of the box, there's going to be less balls in the box, isn't there? So if every time one of these decays and becomes more stable, if I took a ball out of the box and put it somewhere else, the unstable atoms, the balls in the box, would decrease over time. But it's a random process. You're never going to be able to predict when one of them is going to go, or how many of them are going to go once, or whatever. So it follows a bit of a strange shape. If I was wanting to plot that on a graph, so this is the number of unstable nuclei, right? The number of unstable nuclei is the plural for nucleus. The number of unstable nuclei is going to go down over time as they become more stable and emit radiation. So if I put time on this axis, what actually happens is this. Like that. We call it an exponential decay. It drops off quite rapidly. Something's very radioactive, it drops off massively, and then it sort of tails off a little bit. Now, this relationship can allow us to work out the lifetime, or the half-life, of a sample. And that's really important because it tells you how long a sample is going to stay radioactive. Now, some samples, like say for example uranium, can stay radioactive for millions of years. There are elements out there that stay radioactive for minutes. So it's important when you talk about uses, which is the next video, uses and dangers of radiation, that you know what the life cycle or the half-life of one of these samples is. And this is how you do it. So if you've got one of these graphs and you've got a time axis, let's just say this time is measured in days, right? You'll be able to read that on whatever graph you get out of your book or your exam or whatever. The time in days, and on this side we've got, starting off at 10,000, and then halfway down we've got 5,000, and we've got all the bits in the middle, and down here we've got 2,000 and 0. You'll have all the bits in the middle as well. And we've got 10 days, 20 days, 30 days, 40 days, 50 days, all there. Okay? If you read off on your graph, at 10,000, it's got 10,000 unstable atoms at that point there. So if you read that off, and let's just say it comes down as 7 days, it's going to have halved when it goes down to 5,000, isn't it? So it's gone through a half-life. So it goes through to 5,000, follow that down, let's just say that's 15 days. Between 7 days and 15 days, it's now become half more stable. So it's gone through a half-life. The number of radioactive atoms, unstable nuclei, has gone down by a half. So between 7 and 15 days, it's gone through a half-life, and that is 8 days. So in this case, 8 days is the half-life of this particular sample. But you can monitor this a little bit more closely by going from 5,000 again. So 5,000, we go down to 2,500, which is half of 5,000. You could read that across and read that down, and that will be another 8 days. That's why it forms this shape, because it will always be the same period of time in which it halves, forming this exponential decay curve. Now, that might be quite complicated for some people to get their heads around. The only thing you really need to know is it forms this shape of graph, that stuff doesn't stay radioactive forever, it has a half-life. And you need to be able to read off some numbers from a graph to say what the half-life is. And they're usually really simple numbers, especially at GCSE, from 10,000 to 5,000, or 20,000 to 10,000, or 1,000 to 500, something like that. And then you just read the time off. The key to this is reading the scale correctly. You need to make sure that you read the scale correctly, because if this is in seconds, don't put days, it's in seconds. It's always dependent on the scale on the x-axis. Okay? Now, half-life is really important, like I said, for uses and dangers. When we talk about uses of radiation, when you're injecting something into your body, it's very important that you choose something with a short half-life. And you're probably going to be able to guess that it's because if you inject something into your body, you don't want it to stay radioactive for years, because it's going to give you cancer. You want something that's, the radioactivity is going to drop off massively within the first few hours. So you want something that's got a half-life in maybe minutes or hours or something like that. So you can do whatever you need to do with the radiation, and then the radiation is gone, it's pretty much decayed away. There are other uses for things like long half-lives and whatever, but we'll talk about those when we get to the uses and dangers, and we'll talk about something called carbon dating. Okay? So that's the half-life. That's video 3 of the Flipped Classroom project. You're going to have some work to do on the half-life, and in the lesson you're going to have a play with a piece of equipment called a protractinium generator. So be prepared for that. If you want to know what that is and get a bit of a preview so you know in advance, then it's worth Googling. It's a good thing, it's a good practical, and it will demonstrate the half-life really, really well.